This is a terrible picture, but it's trying to show Kepler's third law. So what I want to do is to use gravity and circular motion, centripetal acceleration, to show that Kepler's law is true for circular orbits. If it's not circular, it's not quite as easy. Just letting you know. Okay, so Kepler's third law says that if planets are orbiting the sun, there's my sun, here I have two planets, and I time the time it takes to go all the way around, it doesn't matter what units it's in because it's a ratio. If I time the orbital period for planet 1, the orbital period for planet 2, the square of their periods, the ratio of the square of their periods is equal to the ratio of the cube of their orbital radiuses. That's what Kepler's law says. Okay, so let's just do this, set this up for a planet. I'm going to erase this because I really started off with a bad space, but I am going to put it up here. So I have t1 squared over t2 squared equals r1 cubed over r2 cubed. Now, in general, we use lowercase t for time and capital T for tension, which I know is dumb, and the orbital period. So again, the period would be the time it takes to make one complete orbit. So let's just draw one orbit right here. That's a pretty good circle right there. I mean, it's not bad. There's my sun. Here's my planet. It's moving with some velocity v right there, and it has a radius, orbital radius r1. This is planet 1. Okay. I'm going, why does that planet move in a circle? It moves in a circle because it's got a gravitational force pulling it in this direction. And remember that in order to move in a circle, you have to have an acceleration pointing towards a circle caused by that force. So it all works out. Let's call this the x-axis. I like to do it this way. It's not the best, but it matches up with other things. So at that instant, there's only one force acting on the planet of mass m, and this is the mass of the star, mass s, the sun. It's the sun, okay? And then that's the radius. So the one force is the gravitational force in the negative x direction. So I can say this, F net x equals m ax, right? And then the net force is going to be negative g, mass of the sun, mass of the planet, over r1 squared. That's the gravitational force. I have to use the full gravitational force. And that's equal to the acceleration, which is also in the negative direction. And then it has a centripetal acceleration of v squared over r, and that's r1. So there's my net force, mass times acceleration. Let's convert this. I don't care about the velocity. I care about the time. And I care about the time to go around once. And so that's, I don't know the distance of it. I could calculate that if I wanted to. But it'd be easier to deal with this in terms of the angular velocity. Because I know if I have the angular velocity, the angle for one orbit is 2 pi radians. So remember that v equals omega times r. Sorry about the squeak. So I can put that in up here, and I get the negatives cancel. G, mass of the sun, mass, over r1 squared equals mass, and then I get omega squared r1 over r1. So I get omega squared r1. So that was squared divided by that. Okay, so those mass cancels. The mass of the planet cancels. And again, that's only true for 1, circular orbits. 2, and this is something, orbits in which the sun does not move. Okay, which technically it would, and that's how we detect extrasolar. One of the ways we detect extrasolar planets around other stars. Kind of awesome. Maybe we'll talk about that later. Let's solve for omega. And this is omega 1. This is the angular velocity to go around once. So I'm going to just divide both sides by r1, and I get omega 1 squared is equal to g, mass of the sun, over r1 cubed. I don't care about omega. I care about the angular period, the orbital period. So omega is equal to 2 pi over t, right? Because the angular velocity is the angle, which is 2 pi radians, divided by the time, which is the period. So I could replace this with 4 pi squared over t1 squared. And you can see we're getting somewhere right now. Now I'm going to go ahead and redo this for another planet over here with an orbital radius r2. It's the same math, right? I don't need to do all this stuff again. I can just rewrite this and say omega 2 squared is 4. No. I'm going to do the same equation. I can write the same equation, but except for orbit 2. So I have g mass of the sun over r2 cubed equals 4 pi squared over t2 cubed. It's the same thing, right? It's the same thing. It's the same thing. Okay. So now what I want to do for both of these equations, I'm going to, let's say, I'm going to multiply this by t2 squared, and I'm going to divide by that. Okay. So I get t2 squared over r2 cubed equals 4 pi squared over g ms. Right, that just comes straight from here. Now, what if I did that with that equation right there? I'm going to do the same thing, right? I can do the exact same thing. So let's do the exact same thing. I'm going to get t1 squared over r1 cubed equals 4 pi squared over g mass of the sun. But now you notice that this is a constant that's equal to that, so that this has to be equal to that. So t1 squared over r1 cubed equals t2 squared over r2 cubed. And now I can just cross multiply, which I hate to say, but that's actually what you end up doing. I get t1 squared over t2 squared equals r1 cubed over r2 cubed. The end. And if this is in years, that's fine, because you're doing years over years. The units don't matter, it's a ratio. And same thing over here. You can use astronomical units, AU, which is the distance from the Earth to the Sun, which they used because they did this. When they did this, they didn't know the distance from the Earth to the Sun, but they knew all the orbital radiuses of the planets based on that. So that's how it works. Kepler's third law. There you go. Okay, the end.